Okay. All right, then let's get going here. All right, so there's quite a few problems on here today, so it's unlikely I'll be able to finish all of them. But numbers 2 and 3 are the important ones. So I'm going to definitely make sure to talk about those. So those ones we will get to. And I will point out that problems like numbers 2 and 3 are things that Dr. Gann likes putting on quizzes. So pay special attention to numbers 2 and 3. Okay, here we go. All right, so problem number 1 is all about chain rule. So we've entered the realm of chain rule. And when I say entered the realm of chain rule, I mean at this point, assume that every single derivative you take needs chain rule, because you'll probably be right. Okay, so let's get cracking here. So we have this function y equals 1 minus 3x all raised to the 5th power. So this is a chain rule, right? There's a power rule on the outside and then a nice linear function on the inside. And we're using dy dx because we're written as y equals. So the power rule happens first. And then we multiply by the derivative of the thing inside. And as always, we don't need to simplify anything, but if it's just your basic multiplication, it's not too hard just to write that down. Okay, so there's the first one. Nice little warm up to get us started. Right. As always, if you have questions or you see me write down something that's not true, let me know when it happens so I can address it. Okay, part B. First thing to notice here is the square root really is a 1/2 power. Right. If we can make the function look easier to differentiate, we should do it. So the square root of x squared plus 1 really looks like x squared plus 1 to the 1/2. And now we're back in just like what we did before in part A. All right, so the power rule happens first. So that 1/2 comes down. And then we multiply by the derivative of the inside. So the derivative of x squared plus 1 is 2x. And again, we don't have to simplify it. You can if you want to, or you can just leave it this way. Either way is acceptable. Right. Okay, part C. All right, another chain rule. Okay, except the chain rule now is on this secant. So secant cubed, so that's a power rule. So that's going to happen first. So we'll have the 3 come down. All right, derivative of secant is whatever it is, all these trick things, secant tangent. Yeah, that makes sense. Actually, hang on a second here. Okay. All right, so that power rule happens first. Then we multiply by the derivative of the inside. The inside is going to be the secant of x to the 5th. So now we have a derivative of secant, which is our secant tangent. So secant x to the fifth times tangent of x to the fifth. And then one more chain rule, because there's one more thing inside, right? There's an x to the fifth inside of everything, so we have to multiply again by the derivative of the piece inside there. So this is a double chain rule. All right, so chain rule really just says start on the outside, work your way in. Okay. And again, if we want to simplify this, we can, but we don't have to. So by simplify, I mean, right, we can multiply 5x to the fourth times 3. There's a secant here and a secant squared there, so altogether there's a secant cubed. If you want to do that, you're more than welcome to, but it's not necessary. Okay, questions about the first 3?
Yeah, I have a question.
Yeah.
Can you explain again how you got the secant tangent in part C?
Yes. So let me do some notation here. All right, so this term here comes from power rule. This one came from taking the derivative of secant. And then this one was the derivative of x to the fifth. That's where those 3 pieces come from.
Okay, but if you have a power rule,
Mm-hmm.
wouldn't you have a term that's plus, like adding something?
That's product rule.
Oh, okay. Thank you.
Yeah. Yeah, so this is just a complete composition of functions. There's no multiplications happening. Okay, good question. Any other questions? All right. Okay, so number 2, we did something like this last week, right, where they're just given some random function that's defined by some other functions, and all we know is what it does at certain values, and we have to figure out what this other function is doing. Okay, so I'm given this function p of x, which is defined as the function g compose f of x. I want to find p of 0 and p prime of 0 given things about f and g. Okay. So the first thing that I like to do, just because I'm not a huge fan of the circle composition notation because it doesn't make clear what actually is happening. So this g compose f of x really says g of f of x, right? It says do f first and then do g, right? So parentheses, right? Start on the inside, work your way out. So p of 0 then is g of f of 0. And I know what f of 0 is. F of 0 is 1. So this is going to be g of 1. All right. And lucky for us, that's the information that we need. Right? They told us what g of 1 is. Okay, so that's another way to check that you're doing this stuff correctly, that you use every piece of information that was given to you. And g of 1 is 2. Okay. So that's the first part, just to get us in the habit of, or just in the mindset of this composition of functions. All right. So that's the first part. Now we have to take a derivative. Okay, so we actually have to remember what chain rule says in general. So p prime, and we'll just do p prime of x first. All right, so chain rule says that I take the derivative of the function on the outside, so g prime of f of x, and then I multiply it by the derivative of the inside, f prime of x. Okay, that's chain rule. Okay, so now I just need to know all these other values. So I plug in 0. And when I plug in 0 for x, I plug it in everywhere I see an x. All right, so I need to know what f of 0 is. I need to know what f prime of 0 is. Well, I know what f of 0 is. F of 0 is 1. We knew that already. And I need another color. Use this one for f prime of 0. F prime of 0 is 9. Okay. So now I have to figure out what's g prime of 1. And oh, that's the other piece of information. It's the last piece of information we haven't used yet. All right. G prime of 1 is 5. And yeah, we'll just use this one. And last time I checked, 5 times 9 is 45. So all of this coming just from knowing what chain rule does in general. All right, and this is one of those problems that he likes to put on quizzes. So if there's something about this problem that is unclear, this is the time to ask questions. So any questions about this problem? Okay. Apparently I thought I needed more room for that one. Oh well. All right, number 3. Similar type of problem. All right, we're given this function f in terms of this function h, and we're also given g in terms of a function h. And we want to find the derivative of f and g evaluated at certain points. Okay. All right, so we'll deal with the f prime first. So in order to compute f prime of 7, I need to know what f prime of x is. So we take a derivative. All right, and there's going to be a chain rule here. So f of x is e to the 3 times h of x. All right. So derivative of e to the 3h of x, start on the outside. So the outside is the e to the x. That's the big thing that's happening. And the derivative of e to the x is just itself. So it's e to the 3 times h of x. And then we multiply it by the derivative of the inside. The inside is going to be the exponent. And the derivative of 3h of x is 3 times h prime of x. Right, derivative of a constant times a function is the constant times the derivative of the function. Okay. So there's my derivative of f. So that means if I want to then find f prime of 7, I plug in 7 everywhere. So you get e to the 3 times h of 7. multiplied by 3 times h prime of 7. H of 7 is given to us. It's 2. And h prime of 7 is also given to us. It's 4. So then we put all this together and say this is 12 times e to the 6. And we don't get calculators, so we're just going to leave it like this. All right, questions about this problem? Okay. Now we'll do g prime. So in order to calculate g prime of 2, I need to know what g prime of x is. All right, so this time h is on the outside. Okay, we're looking at this now. So h is on the outside, so that's the derivative we take first. So we get h prime of e to the 3x multiplied by the derivative of the inside. So multiplied by the derivative of e to the 3x, which itself has another chain rule. We multiply by the derivative of e to the 3x. So the outside function is the e, so we just get itself. And then multiplied by the derivative of the inside function, which is the exponent. So the derivative of 3x. So this has a double chain rule. Okay, now I need to figure out what g prime of 2 is. And so I just plug in 2 everywhere. And I get h prime of e to the 6th multiplied by 3e to the 6th. So I need to know what h prime of e to the 6th is. Oh, can you show the chain rule part for the second one? Yes. So this is h prime of e to the 3x multiplied by the derivative of e to the 3x. So we get this that's why it's called chain rule. We get a chain of derivatives. Start on the outside and work your way in. So h happens first, then e, then the 3x. Okay. So I need to know what h prime of e to the 6th is. And wouldn't you know it, they told us. Oops, that one. It's 9. So altogether we got 27 e to the 6th. All right. Questions? Okay. All right, so number 4, all right, we're taking more derivatives, but now we have potentially implicit differentiation. So now that we understand how to do chain rule, we can move on to this thing called implicit differentiation, where the x's and y's aren't written in a nice way, right? We don't have y equals potentially. We have x's and y's that are stuck together and there's nothing we can do about it. So we have to use what's called implicit differentiation, where our dy dx might have y's in it when we're done, which is okay. All right, so this first one, all right, we got y equals 2 to the x. Okay, and there's 2 ways to do this. All right, we can use what's called logarithmic differentiation, okay, or number raised to the x power has a derivative formula itself. Either way is fine. Personally, I like the logarithmic differentiation one better because it stops you from thinking that maybe you have a power rule, right? This is not power rule. Okay, not power rule. The x shows up in the exponent. All right, it's number raised to the x power. Power rule is x raised to a number power. All right, so logarithmic differentiation just means you take a natural log on both sides and then take another derivative. All right, and then just take the derivative from there, and then nice things happen. Okay, so we're going to rewrite this as natural log of y is equal to natural log of 2 to the x. Then we use our logarithm rules that say, hey, that exponent just drops down in front. All right, now we take a derivative. And I'm going to be very explicit about this. All right, so we take a derivative with respect to x on both sides. Okay, so derivative of natural log is 1 over. So this becomes 1 over y. But I took a derivative of y. When I take a derivative of y, we have a dy dx. On the right-hand side, I take a derivative with respect to x of x times natural log of 2. Well, natural log of 2 is just a number. So this really just looks like number times x. Derivative of number times x is just the number itself. Okay, I want to solve for dy dx because that's what the problem is asking for. So it's going to be multiplied by y on both sides. I'm going to get a y times natural log of 2. But hey, I know what y is. It's 2 to the x. So we get that dy dx is equal to 2 to the x multiplied by natural log of 2. And if you remember that little formula for the derivative, this is actually exactly what the formula says. All right, something's happening in the chat. I got a private message in the chat. So I think I said this before. If you have a question to ask to the class, please do. All right, that was the question. Why do we add dy dx? dy dx happens because I took a derivative of y with respect to x. That's what the dy dx says. All right, it says derivative of y with respect to x. That's what those letters mean. Okay. Over here, when I took this derivative, I'm taking a derivative of x with respect to x. So I mean, I can write that down as derivative of x with respect to x, but that's just 1, which is why we don't write it down when we take a derivative of x. So dy dx shows up when we take a derivative of y. Okay, that will become much more apparent in this next example. Okay, so part B, we've got sine of x plus y is equal to x times y, and I want to find dy dx. Notice there's nothing I can do to make this thing look like y equals stuff to do with x, because this x plus y is stuck inside of the sign. I can't do anything with this. All right, so I have to use implicit differentiation. All right, so we take a derivative on both sides. Okay, on the left-hand side, we're going to have a chain rule, right? Because we have a sine on the outside and then some other function on the inside. So on the left-hand side, we take derivative of the outside first. So derivative of sine is cosine. All right. And then we take the derivative of the thing on the inside. The derivative of the thing on the inside, and you know what, I'm just going to be super explicit and write everything down. So the derivative of the stuff on the inside is x plus y. So I have to take a derivative of that with respect to x. Okay, let me finish this left-hand side before we jump to the right-hand side. So I get this cosine of x plus y, derivative of x plus y with respect to x. So the derivative with respect to x of x is just 1. And the derivative of y with respect to x is exactly the derivative of y with respect to x, dy dx. Okay. Any questions about that left-hand side before I move on to the right-hand side? Okay. So on the right-hand side, we have a product rule. Right? Derivative of x times y, product rule. So product rule says I take the derivative of the first one and multiply it by the second one. And then I add the first one multiplied by the derivative of the second one. Okay. That's product rule. Now I take my derivatives. Derivative of x with respect to x is just 1. 1 times y is just y. Derivative of y with respect to x is exactly dy dx. Okay, so the product rule still happens. All right. So at this point, right, I want to solve for dy dx. So I just need to do some algebra. Okay, so I want to get everything that has a dy dx on one side and then not dy dx on the other side, and then factor it out and divide, right? Just solving for dy dx. Okay. So let's see here. So if I distribute this cosine into here, I'm going to get a cosine x plus y times dy dx. So there's going to be one piece with the dy dx. I'm going to have this x with the dy dx on it on this side. So that's going to be the stuff with dy dx. Right? One of them I'll have to subtract. Doesn't really matter which one. So let's say over here we have cosine x plus y minus y. And then on the right-hand side, we'll have x. I'll factor out the dy dx now. I have an x minus cosine x plus y. Okay. And then solve for dy dx. So I'll have cosine x plus y minus y divided by x minus cosine x plus y. And we'll put a nice box around this just to make it clear. Okay. All right, so this is a case where dy dx is going to have x's and y's in it. There's no way around it, okay, which is why in the problem statement, we're allowed to have this thing in terms of x and y. All right, questions? Where the x minus cosine x plus y came from? Yes, so I distributed this cosine to both. I kept the cosine times dy dx. No, I'm sorry, I kept the cosine x plus y times 1 on the left-hand side. So that's where this one came from. And then I subtracted the cosine x plus y times dy dx over here. It's just the algebra and solving for this thing. Yeah. Okay. Other questions about this problem? Okay. All right, number 5. We want to find the slope and the equation for the line tangent to this curve. And this curve is written in a bizarre way. Okay, the first thing is, what is the slope, right? How do we use calculus to do this stuff? So we'll recall that the slope of the tangent line at the point -2, -3 is the function dy dx evaluated at the point -2, -3, right? Dy dx, the derivative, tells us the slope of the tangent line. That's what it means. Okay. That's the meaning of the derivative. The derivative is a slope of the tangent line. All right, so I need to find dy dx, okay? Because after that, we're just trying to find the equation of a line, and the equation of a line, we just need a slope, and we need a point. We already have a point, so really we just need the slope. Once we have that, we're good to go. So I need to find dy dx. Okay, so we'll take a derivative on both sides. Right. The right-hand side is easy. It's going to be 0, right? Derivative of a number is just 0. So I'll do that one last. So derivative of x squared plus xy plus 2y squared, right? There's 3 pieces here, okay? One of them is a product rule. So again, I'll be very explicit. Okay. So this first one, derivative of x squared, that's just our good old 2x, right? Derivative of a function of x we know how to do. Derivative of x times y with respect to x, right? That's a product rule. We've done it before, so I'm not going to write down all the little steps in between because it's up above. So I'll just write down exactly what we did before. And then derivative of 2y squared with respect to x, okay, has a chain rule. There's a chain rule here. All right, so there's a power rule that happens first. Okay, we get 4 times y, but we took a derivative of y. So we need to indicate that we've done that by multiplying by dy dx. Whenever you take the derivative of y, the dy dx shows up. All right, we don't need to tell anybody that we're taking the derivative of x because everybody's assuming we're doing that anyway. The thing that's different is when we take the derivative of y. Okay, questions up to this point. We've done all the hard work. Because now we're just going to solve for dy dx like we did before, plug in some numbers, and then write out the equation of a line. Alrighty. So let's solve for dy dx. So let's see. Things that have dy dx are x and 4y. And things that do not have dy dx are a 2x and a y, but I'll subtract those to the other side. Okay, so one more time. These 2 pieces have a dy dx, so I factor it out, just leaving with x plus 4y. So I leave it over here. These 2 pieces do not have dy dx, so I move them to the other side. And when I do that, I have to subtract them. So they become negative over here. So then dy dx is going to be minus 2x minus y divided by x plus 4y. Okay, now to find the slope, I have to evaluate this thing at the point -2, -3. Slope is dy dx evaluated at the point -2, -3. So I plug in -2 for x, I plug in -3 for y, and see what we get. So we're going to have a -2 times a -2, subtract a -3, all over -2 plus 4 times the -3. And what do we get here? 7 divided by -2, -12, -14. Whoops, that's not right. What am I doing? I should just write it down. No, I'm right. 7 minus 14, also known as -1/2. All right, so that's my slope. So now I have a slope, I have a point. So the equation of my line y minus -3 is equal to -1/2 times x minus -2. Easiest way to write the equation of a line when you're given a point and a slope is point-slope form. Questions? Okay. All right, so we got about 5 minutes left. I will start on this one. I don't think I'll finish it, but I'll start. So number 6 really is just, above and beyond chain rule stuff. All right, so finding the derivative of this function x cubed times e to the x squared, there's a product rule and a double chain rule. Okay. So f prime of x, and because there's all kinds of crazy stuff running around, all right, so a product rule is going to happen first because it is the product of two functions. Then there's going to be a chain rule when we get to that e to the x squared. Okay, so product rule says I need to take the derivative of x cubed and then multiply it by e to the x squared. And I add x cubed multiplied by the derivative of e to the x squared. All right, derivative of x cubed is 3x squared multiplied by e to the x squared. First term's not too bad. Second term, we've got x cubed multiplied by derivative of e to the x squared. Now there's a chain rule. So I need the derivative of the outside function, which is the e function. Okay, so that's the e to the x squared just by itself. And then I take a derivative of the inside function, which is the exponent, derivative of x squared. And the derivative of x squared is 2x. All right, so this is like, yeah, above and beyond with chain rule. All right, questions about this one? Okay. Guess that one didn't take nearly as long as I thought it would. That's good. All right. This last one, see if I can do it in 2 minutes. So our function is x to the 1 over x power. All right, it's not a power rule because there's an x in the exponent, but it's also not that standard number raised to the x either because there's an x in the base. So the only way that we can really handle this thing is using that logarithmic differentiation that we did before. All right, and that logarithmic differentiation says to take natural log on both sides, then take a derivative. Okay. And then you'll notice pretty quick that on the right-hand side, when we take this derivative, we're going to have either a product rule, which is probably the easier one to handle, or a quotient rule. Okay. And I'm going to run out of time trying to do this, but I will. And on the left-hand side, we have a chain rule. Okay. All kinds of fun stuff happens. So we take a derivative on both sides. Right, on the left-hand side, there's a chain rule. So the outside function is the natural log. That happens first. The inside function is f. So we'll take a derivative and get my f prime. On the right-hand side, I'm going to call this a product rule. So this first function, 1 over x, is actually x to the minus 1. So its derivative is minus x to the minus 2. And then I'm going to add 1 over x multiplied by the derivative of natural log, which is another 1 over x. Okay, now I'm trying to find f prime, which is sitting right here. So to solve for it, I need to multiply f of x to the right-hand side. So f prime of x is going to be f of x multiplied by minus x to the minus 2 times natural log of x plus 1 over x squared. And this is where, right, trying to simplify things is really not a good idea. And I already know what f of x is because they told us. So we'll just make that replacement. Okay. So I went a little over time, but that's okay. We got everything finished. So this will get posted after class. As usual, if you have any questions about any of these problems or anything else, send me an email, come see me in office hours, all that good stuff. Other than that, have a good rest of your week, and I'll see you next week.